Too much technology. Now, where is my dog? Too much technology. Now, where is my dog?
Sir, sir, wait.
You have to open the top. You have to open the top.
It's closed. Yeah, it's closed.
What happened?
It's closed. I want your talk, sir.
Close,
Your talk.
talk. Your presentation, yeah.
Huh?
Your presentation next.
What do you want me to do?
Open.
Your talk, sir.
You have to open the talk. Open your presentation.
Okay.
Somewhere.
One second.
I lost it.
What is the name of your talk? Name of the talk?
What is the name of the talk, sir?
Name. What is the
Yeah,
name?
yeah.
Yes.
I'll do it.
This IMSC 24 April 24.
Desktop, sir.
Desktop.
There we go.
Yeah.
Full
You have
screen.
to-
1 second.
Let me begin. So it's really a great pleasure to have Mr. Ajaz with us. I'm sure most of you know, he doesn't need an introduction. I mean, for those who are interested in the audience. He was our professor here for a very long time, and he was my teacher too. So I learned my PhD from him. So with that knowledge here. And he's not only a great teacher, he is also good in textbooks or books on specialist topics. He has written several books. And I take this opportunity to actually introduce sort of release the book actually to library, and he is going to do that. So I request Madhu Pandi to
Make it full screen.
yeah, we'll do it. This book that we wanted to release.
Huh?
The book.
Yeah. So, thank you very much. I'm very happy to announce this book, which took me 3 long years. It's called Strings to Strings, and there's a reason for that. And first of all, it covers a lot of stuff, but it was written during COVID period, and also in the middle after in Mysore. So this is all added to the difficulty of writing this book. And in Mysore, I didn't have good library. In fact, I had 0 library facilities. So, so I had to rely almost entirely on IMS library. And Pandian was extraordinarily supportive. Within an hour or two of my asking for a paper, he would have the PDF ready. And these papers were not published in recent times. Some of them are very old.
I know.
So this book owes a lot So,
Actually, it's not
I
even
was
my
like-
machine, so I cannot.
Even I don't know what is done.
It's probably because it's
If I
and for that
remove,
reason, the token of association.
I see.
Present this book to the IBC library.
I had
just
But I would like to
even
say
I don't
two
have
things
anything,
more
this
about
is not supporting it.
IBC library. Online.
Okay, maybe
Wonderful
after his
library.
book release,
But I
just
can't
ask
say
if there is
86.
anybody who knows.
The most striking thing to me was what a wonderful library this institute had. So Alari Ramakrishnan and others, they paid a lot of attention, both in mathematics and in physics. This library was one of the best I've seen, and I've seen lots of libraries. In fact, the only comparable library that I could think of was the one in Niels Bohr Institute, and somewhat less so in Raman Research Institute. So it was a very pleasant surprise for me to see such a wonderful library. Second point, while writing this book, I had to deal with a topic called the Mandelstam double spectral vector. This played a very, very big role in the development of S-matrix theories, and Mandelstam conjectured it almost 66 years ago, and even to this day, it is not proved. But nevertheless, it was like a beacon in guiding the progress of S-matrix theory. And if you look up most books, you will not find anything on Mandelstam double spectral. So I was searching, and I was very surprised to find a math science report of 1963, written by T.K. Radha, entirely devoted to the Mandelstam representation. And it's available as a math science report. So this shows the tradition that this institute has followed, in more than anything, what the academics need is a very sound library. So in token of my appreciation, I present this book to you. So, can we make this
Yeah,
full screen or
we have already made
I have to do it.
screen in the machine, but we connect it to a particular exactly.
No, I can't change it here.
I just got it also. No, it's it's interconnected or it should like this machine.
So shall we do with this or?
You can take PDF and put it in that, whatever that you can. Yeah, maybe you can. You put it in that.
Can you give us the PDF file, then we can actually try to open it through the machine.
One second.
You can take it.
Full screen இருக்கா கனெக்டர் போட்டா அங்க full screen போயிடும்.
Let me start telling you.
வர
So
மாட்டேங்குது.
this topic,
இப்படி ஆயிடுது. நாங்க என்ன பண்ணாலும் move ஆக மாட்டேங்குது.
connection between superconductivity and
Touch ஆகணும்.
why did I choose this kind of topic?
நார மட்டும் செய்யுது.
For quite some time now, I've been trying to convey that our teaching.
Control L. Full screen ல தான் இருக்கு.
Nature makes a cell, it doesn't say, oh, this part is physics. And let me call the library.
எடுத்துடலாம்.
This division is our teaching for a very good reason, because all the masters in every, so we branch off, and this is becoming more and more narrow.
Alphabetல தான் இருக்கு.
Even though that's the practicality of the situation, we have to be aware that science is uncompartmentalized. And take every opportunity to convey to students that this essential connectedness of science. In fact, if we had made if physicists are aware of chemistry,
ம்.
I think quantum mechanics
Awesome.
are the
இருங்க
physical problem.
ஆஸ்பிரின் கொடுத்தா வர மாட்டேங்குது.
Because many things that happens in
ம், பாருங்க.
chemistry, they are impossible to realize in a classical world. Like the whole concept of reality of a stable orbit charge that moves across two charge centers. There is no stable orbit in classical. Like that. And in fact, Dalton's work eventually led to the notion of isotopes to Aston's work. I can go on giving many examples. So I feel that every now and then we have to drive home the point that what we think are very different, there are connections. And I chose these two because traditionally condensed matter physics. Few people realize the interconnectedness, but many think of them as very separate disciplines, and even there is some meaningless rivalry between condensed matter theories.
மேடம் ஒரு இடத்துல செக்யூரிட்டி கேட்கும் ஸ்கிரீனை ஷேர் பண்றதுக்கு
To dispel that,
Yeah.
I've chosen this. So
ஸ்கிரீன் ஷேரிங் இருக்கும்.
ideas in superconductivity in great detail, not in some allegorical level, influenced major developments in politics. So that's the thing. And my talk is still not surfaced.
இப்ப நம்ம இதுல பொருளாதாரம்
Yeah, good. And I can use that
Yeah, you
to
can
go
use
up and down.
yeah, you can go down.
So that's the title, Superconductivity and Particle Physics. The beauty, unity, and power of physics is my theme. Now, as I already said, sciences have become highly compartmentalized. And the reasons are historical, methodological, practical. But this has also led to all kinds of unwanted biases. Like when I started my undergraduate study in Delhi University, we were told only physics is worth studying, and in physics, particle physics at the top, blah, 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 etc., and electronics at the bottom. Chemistry, don't talk about it. There will be all kinds of jokes, that, there are these two girls. One of them says, oh, here comes the physical chemist. The other one says, how do you know? Yes, by all the holes in his clothes, we know he's a chemist. But then she says, yeah, but what about the physical part of it? And she says, at the drop of a hat, he gets physical. So there will be all kinds of jokes about chemistry, not to be taken seriously as a profession. This is very, very bad. Because we never really appreciated the true depth of chemistry. But as I said, the need to keep reminding ourselves of the essential unity of science, but in this talk of physics, is urgent. Now, what is important aspect of this unity is science's ability to relate the unthinkable. What we think are no relationship to each other, science finds a way related to that. So there is a saying that what God has joined together, let man not put us under. This is a biblical saying. So I would say what nature has joined together, let not scientists pull us under. Okay? So let's try and think of science as one whole as far as possible. So relating the unthinkables. Here is the most classic example of what most people would think are unrelated, unthinkable to relate them. The falling of an apple and the movement of the mood. And I think the biggest failure of science journalism today is that most people still don't make this connection. So they have failed to communicate the essence of it. And this is because science journalism, like TV ratings, also goes for sensational things beyond the standard model, traversable wormholes and so on, and doesn't give enough importance for propagating. This is a very, very beautiful chapter in science. And in fact, I have read Newton's reasoning several times, and it is amazingly beautiful. So that's the general message. So I will talk about another grand connection, and that is between superconductivity and elementary particles. So it takes extraordinary mind to make this connection. Just as Newton made this connection. And the connection between superconductivity and particle physics was essentially due to the work of Yoichiro Nambu. And he wrote these two papers, Dynamical Model of Elementary Particles, based on an analogy superconductivity with journalist syndrome. And the two papers still continue to influence many people. Students who are interested in seeing this in some detail, I recommend them to read my article I wrote for Resonance long ago about Yoichiro Nambu. So that is how the connection began. But in order to appreciate it, you need to know what superconductivity is and what particles are. And I will try to convey the essence of both of them without going into too many technical details. I will not evaluate Feynman integrals and do renormalization or do a many-body calculation. I'll try to present the essence of superconductivity and why it plays this incredible role. Superconductivity was discovered 1911 in Holland, where I was fortunate to spend many years. And on the one on the right, the bald-headed man is Kamerlingh Honest, and it was in his lab this was discovered. There are all kinds of folklore about how a student fell asleep while taking measurements, and when he woke up, he found that resistance had hit through the ceiling. Like just as there's folklore about how Newton discovered gravity because an atom fell on its head. These folklores are not important. In fact, Vishweshwara is a version where gravity was actually discovered in Kerala. The coconut fell on a Nambu's head, and before he could publish, he had perished. Many of us perished after publishing. So, Honest had this phrase, and I want to share that because these days we fight a lot about this language, that language. It's silly because we should know as many languages as possible. Because words, they don't have one meaning. When you utter a word, a whole lot of cultural and other associations come, and it is that entirety, which is the word. So in different languages, the expression of the same thing, takes different forms. So Honest said, "Dormete tot waiter." That means maintain is measure, waiter is to know. Sounds very cute. But in English, if we say by measurements to knowledge, just don't have the same lilt. So in 1911, the superconductivity phenomenon was discovered. And what is it? They were looking at mercury, and what was found was that when mercury was cooled very, very sharply, the resistance fell and it disappeared. Within the resolution of the measurement, there was no resistance. So, honest, that quick, no, quick means quicksilver, and he says it's almost zero. The resistance of mercury has become almost zero. Now, how is this possible? Related to this, honest also established something called persistent current. If resistance goes to zero and you set up a current, there are no ohmic losses at all, and the current can persist for a very, very long. Okay? And he even measured persistent current almost immediately after seeing the vanishing of the resistance to see how remarkable it is. Already in 1963, Simon Mills, I don't know whether it's the same as Robert Mills of Young Mills, they observed persistence for almost 150,000 years. And I'm sure today you can set up persistent currents which will persist for much, much time. This is striking phenomenon of vanishing resistance and persistent currents.
What does it mean? They observed it for 120,000 years. Persistence for as long as 100,000 years. What does that mean?
Well, it's the same as saying Feynman in his book, he says, lady, you're driving at 60 miles an hour, and he later apologizes for the lady, you man. And she says, but I haven't been driving for 1 hour. So what does 150,000 mean? Is that you measure some drop and extrapolate how long it would take to completely vanish. Another important effect, which was discovered by Meissner and Oxenfeld, called the Meissner-Oxenfeld effect. And this was discovered in 1933, 22 years after Honest discovered superconductivity. And the experiment roughly went as follows. You start with a ball of material, which is a superconductor. Now, this sharp fall in resistance happens at a temperature, and that's called the critical temperature. So you first take the ball to be temperature higher than the critical temperature, and you apply an external magnetic field. You have a situation like that, and then you cool the sample below critical temperature. And what they found was that the magnetic field was completely expelled from the sample, and it rearranges like that. Now, there's a difference between a superconductor and a perfect conductor. In a perfect conductor, the rate of change of magnetic field is zero. In a superconductor, the B field itself vanishes, and they're not the same. Now, how does it happen? Clearly, what must be happening is that the currents which are set up inside the superconductor and the magnetic field due to the current is such that it exactly cancels the field in the interior and discharges the magnetic field outside. And these are again the persistent currents that we already talked about. There is a small technical difference which is important. B doesn't actually get expelled totally. it penetrates to a very small depth, called the penetration depth. Okay? And we will later see that this has a very important interpretation. Connections with particle physics. Not only the vanishing of the current aspect of superconductivity, that's so important, but Meissner. You see the implications of Meissner effect on the ones that have deep lessons for particle physics. So basically, this is the Meissner effect. Here is the magnetic field, and in an ordinary conductor, the magnetic field can penetrate, but in a superconductor, it's completely expelled. And as I already said, this can be understood as currents being set inside the superconductor, which produce that. There's also something called magnetic levitation, which is very beautiful phenomenon, where you take a superconducting sample and place a magnet over that, and when you adjust things properly, the magnet just floats. And levitation is held the imagination of people. I remember Charles Physician, who was the director of the institute, once gave a talk at IISc. He used to be a fond follower of Maharishi Maheshwari. And the claim was that Maharishi Maheshwari transcendental meditation can make people levitate. And he even showed pictures, look like people were levitating. And you never could tell whether George was serious or joking. Because he would also say things like, the only problem they had there was air traffic control, because everybody was levitating and flying around, and you had to make sure that they didn't clash together. Anyway, this levitation is nothing to do with transcendental meditation. Now, let's understand the physics of magnetic levitation. So basically what happens is that here is a superconductor, and then there is a magnet there. And now the superconductor has persistent currents, and it sets up its magnetic field patterns. And the persistent current can be looked upon as a magnet, and you can show that the interaction between these two magnets is such as to ripple each. So that's how the magnetic levitation can be understood, but it is just a corollary of the Meissner effect. Now let's go a little deeper for understanding how can the resistance ever vanish, and for that you have to understand where does resistance come about. And the classic theory was that you apply some voltage, and the charge carriers, which are electrons, because they're negatively charged, the current flows like this, and then the charge carriers are scattered by the medium, and so there is a resistance to the flow of current, and that's the origin of the resistance. So in the superconductor, what happens? You still have electrons, and why is it that resistance goes away, which means somehow these electrons are not getting scattered at all. It's as if, they just move all by themselves. And understanding of this took quite some effort. And an important concept is that of a Fermi surface. So if we take a metal, electrons being fermions, no two of them can occupy the same level. Therefore, in a given situation, they will fill up up to some surface, and it so happens that all scattering can only take place at the surface, because the interior, if you try to scatter with the kind of energies that are available, the final state to which it will be scattered is already occupied, and no scattering is possible. So this is, everything happens at the Fermi surface, but still, that still leads to scattering. Then it was discovered that if there's a gap at the Fermi surface, sufficiently high, then even the scattering at the Fermi surface can get inhibited totally for all practical purposes, and that is how one would understand superconductivity. But this is not enough. The big coup came in 1950. This is called the isotopes. If you actually looked at the critical temperature for different isotopes of the same superconducting material, it was found that there was a relationship of this to the mass of the ion. Chemistry, the mass of the ion hardly ever played any role. And the relationship roughly was that the critical temperature varies as m to the minus a half. And now we know that these ions are sitting in a lattice and they oscillate like a harmonic oscillator. And the frequency of the harmonic oscillator has exactly the same dependence, m to the minus a half. So this showed that lattice vibrations are somehow very important for superconducting. Still, nobody had an idea how important it is. It turns out that electrons, because of being light charged, should be repelling each other, but because of lattice vibrations, they feel a mild effective attraction. And this is hard to imagine, and it requires some thinking, and that mild attraction leads to the formation of a pair of electrons. And now this leads to an instability, because two electrons by themselves versus two electrons bound, there's an instability. They have lower energy. So if you can create a situation where all electrons are through this instability going to pairs of electrons, then you have a dramatic effect, and that is a based on this. So this Cooper pair idea is what really made a big breakthrough. So how do you understand Cooper pairs? So here is a lattice, and now here is an electron, and now because of lattice vibrations, sometimes the ionic charges are closer, and sometimes they're farther out, and this changes the interaction between this electron and another electron, leading to a net attraction. And this can be expressed in terms of the diagram, Feynman-like diagram, where the electron scatters another electron through the exchange of quanta of lattice vibration called phonon, and then you can see that there are regions where there can be net attraction between electrons. Quickly, still there was no theory of superconductivity. And that happened in 1957. Nearly 46 years after the discovery of superconductivity. was formulated by Bardi and Cooper, who formed the idea of Cooper pairs and Schaefer. Now, while single Cooper pairs are easy to understand, this condensation into multitude of Cooper pairs is technically extremely difficult to describe. And that was essential for calculating the gap which we did. So Schaefer, he made a guess for the mathematical form of the many-body wave function. And then from there, one could develop the theory of superconducting. A very nice introduction is given by a small article by Charles Slichter, and I recommend students or others to look at it. But this was 57. 7 years before. And this is going to be very important. Ginsburg and Landau, Soviet Union, they said, we don't have a theory for superconductivity, but let's see how far we can try and describe this. And for the first time in physics, the idea of an effective theory, and Monday we heard a very nice talk by this was one effective field theories. And Ginsburg Landau theory was the first effective theory. What's the idea of the field theory? You keep very few degrees of freedom and impose some symmetry requirements, and then look at the dynamics of this highly truncated degrees of freedom and what can you do. So the degree of freedom that Ginsburg and Landau introduced is called the order parameter. Idea is very simple. It is 0 for normal phase and non-zero for and the transition from vanishing order parameter to non-vanishing order parameter is what the phase transition is. Very simple. You take a function like this. This should be ax squared plus bx to the fourth, where a is positive for t above tc and a is negative for t below tc, and b is always taken to be positive because it's like the Hamiltonian should be bounded. So there's a minima at x for t greater than tc, but for t less than tc, it occurs at a non-trivial value. So if you take x as the order parameter, it changes from 0 above the critical temperature to non-zero value below. Very simple description. Okay. But this missed a crucial ingredient, namely, there is a phase which plays very important. Okay. So if you include the phase into the effective description, you make the order parameter complex. You simply generalize what I had earlier. Now, this is invariant in the global transformation, where you transform the order parameter by a phase where theta is space independent. So it's a global invariance. Important to keep track of that. Then, when the magnitude of f is square root of minus a over b, then the value you get for t less than tc, phase is undetermined. Configurations with different phases are degenerate because the free energy only depends on the magnitude of f and not on the phase. So there is a U1 symmetry. By symmetry, we mean whenever there is a degeneracy. Shortly, I will come to a distinction between invariance and symmetry. Every symmetry is an invariance, but every invariance is not a symmetry. Okay? And this has to be kept in mind. So phase transition chooses one particular value of this phase from a continuum of physically equivalent values. And this is called spontaneous symmetry. So the Ginsburg-Landau effective description got the essence of what is going on, namely that there is a spontaneous breaking Newton symmetry. So here it is. When T is greater than Tc, the free energy looks like that, and the minimum is at 0. When it is less than 0, the minimum occurs at this magnitude, but the phase is completely undetermined, and every point on the circle is completely equivalent, because the global phase, global gauge transformation will go from one point to another. So this is what one means by degenerate vacuum. What about fluctuations? So you expand your F in terms of this minima and plus some small fluctuation, and there should be space here, and then you can see that F goes as A is positive minus U squared, and with our convention, this means these are positive mass fluctuations. Now, phase fluctuations, on the other hand, introduce the gamma gradient F squared with gamma positive. And if you put F equal to F naught into that, and that leads to, for these fluctuations phi, a term like this, with no phi squared term. So the phi field behaves like a matchless field. And these are called the Boltzmann bosons. And in 62, Salam, Goldstone, and Weinberg somewhat formally proved the theorem in field theory that whenever continuous symmetries are spontaneously broken, you will always have massless Goldstone bosons. Classic way of understanding Goldstone bosons is in the Heisenberg ferromagnet, where the Hamiltonian J is positive, is rotationally invariant, and the ground state, when the ferromagnetic ground state, all spins are parallel, and this rotation is spontaneously broken to just one-dimensional rotation around the spin direction. And so this leads to excitations in the system, which are the massless Goldstone bosons, and their energy goes as Q squared. And it's very easy to understand that because in the ground state, all the spins are parallel. And now if you take a wave where one is at a slight angle to the other, there's an energy which is very small. So by making the pitch very large, you can get excitations which are arbitrarily low energy. And that is what we mean by massless. So it's easy to understand why spontaneous breaking of continuous symmetries leads to massless modes. For discrete symmetry like Ising model, you can clearly convince yourself that there can be no Goldstone. Okay. So we are still talking about superconductor. But the amazing thing is, the superconductor, no Goldstone boson was ever seen. Okay. And another related question is, What is the explanation for the Meissner effect? Now, the Ginsburg-Landau effective theory is so simple that it answers both these questions. Clear, straightforward. That's the power of effective theory. In real-life superconductors, there's electromagnetic field, and you can't turn it off. So you must couple the Ginsburg-Landau theory to electromagnetism. Without that, the Ginsburg-Landau analysis is incomplete. But we see that inclusion of electromagnetism results in a paradigmatic change. It's not a smooth change. Changes the description completely. And we got several lessons for field theories. So we'll change the notation. We'll call F psi x. Now we couple, and we'll also allow for, spatial variation of the order parameter, and we couple the electromagnetic field through the minimal coupling, and you see that this is the Ginsburg-Landau theory when electromagnetism is turned on. Now, this has an extra invariance that when psi is changed by a local phase change, this should be psi here, and A correspondingly changed, this doesn't change at all. So now the theory has local gauge invariance. But now there is no more degeneration because the points on the circle, which could be related, 2 points could be related by phase global transformation. Under local transformation, they all become the same state. This is like in electromagnetism, when I make a local gauge transformation, I don't get a new state. It's the same state, because the electric and magnetic fields are the same. Therefore, this is no longer a question of symmetry, because there's no degeneracy of states anymore. The entire circle has to be thought of as one single state. Okay? So it's a very, very important change. No symmetry, but there is invariance. So this is what I meant, that every symmetry is an invariance, but every invariance is not a symmetry. The local gauge transformations are invariances, but there is no symmetry because there is no degeneracy. A more technical way of looking at it is, if you apply Noether's theorem for local gauge transformations, you don't get any conservation law. Okay? The connection between symmetries and conservation laws of Noether's theorem works only for global invariances, which are symmetries. So you can say that conservation laws are a consequence of symmetries, but invariances did not lead to any conservation. So that's why gauge transformations are invariances, but not a symmetry. And I already gave a talk here about this, but still the community refuses to say this extremely fundamental point that you should not talk about gauge symmetry. There is no symmetry associated with local gauge transformation. This is what we call an oxymoron. Oxymoron is when you put two words which don't have any meaning. In the movie, I think is the example as military intelligence. That's supposed to be oxymoron. So gauge symmetry is an oxymoron. Please don't use this when you write your paper next time. If you are tempted to use the word gauge symmetry, remove it and simply say gauge invariance. I already explained this. Now, since there is no longer symmetry, there cannot be any spontaneous breaking. Because there's no symmetry to be broken. Therefore, the phrase spontaneous breaking of gauge symmetry is a double oxygen. To be completely avoided, there is no such thing, and this gets more and more technical, but I promised not to be. So let's get back to the Ginsburg-Landau theory. In the presence of electromagnetism, what happens? The phase phi of psi only occurs in this combination, because remember that comes from the so-called kinetic term, this term here. In these terms, the phase has disappeared. The phase enters the description only here, and the combination is gradient of the phase plus IQ star A. It always comes in that combination. So you can call this C, and in the superconducting phase, the term leads to gamma psi naught square C square. So C is the vector field, is a massive vector. That's what coupling electromagnetism does. You can see that the Ginsburg-Landau physics without electromagnetism, with electromagnetism, dramatically different. And you can work out B, which is the curl of A, and it obeys this equation instead of the Maxwell's equation. This means that B behaves like a massive field, and the mass of that depends on the superconducting density. If you work out the coordinate solution to this, it means B has an exponentially falling dependence. So from outside, it starts falling, very quickly falls, and becomes almost. So this is the penetration effect of the Weissman effect. And this is the way it can be done. So the Ginsburg-Landau theory explains everything. At this point, you really didn't need a fundamental theory. Other things like London equation, etc. So the model for particle physicists is that superconductivity is an abelian Higgs effect. Okay? Of course, standard model involves non-abelian Higgs effect, but conceptually much more abelian. Technically very good. Now I come to particle physics. What's the first impact? The pion. The nucleons in a nuclei are held together by short-range forces. How do you know they're short-range? The whole lot of literature telling you how nuclear forces are short-range, because nuclear forces saturate, blah, 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 blah. And you can even determine the range of the nuclear physics, nuclear force. So Yukawa said the nuclear forces are mediated by particles, which later came to be known as pions, and these are massive. And because of mass, they are short range. But what is surprising is that it's a particle of very low mass. This is a great puzzle. Why is the pion so light? And the number to compare is m pi squared over mn squared, and it's only 2%. So it's as if the pion is almost massive. Okay. Now, currents like electromagnetism, which are vector currents, they're conserved. But naive nuclear axial currents, you can construct an analog of a vector current by adding a gamma phi, and these are far from being conserved, because if you take the divergence of them and do the usual trick, it is proportional to the nucleon mass, which is huge. So then the puzzle here, that while the vector currents are conserved, the axial currents are far from being conserved. So there's an asymmetry between vector currents and axial currents. Now it was at this stage that Nambu entered and proposed a simultaneous resolution of all these difficulties. See, the hallmark of a good theory is that it solves many problems all at once. You don't fix one problem in isolation and fix another problem in isolation. So, this Nambu's analogy with superconductivity actually solved all of them. And he wrote a paper called Axial Vector Conservation in Weak Interactions. And Gelman and Levy, at the same time, they wrote a paper called The Axial Vector Current in Beta Decay, one beta decay. Now, these people proposed an effective theory for pion-nucleon interactions. And that was identical both in spirit as well as in mathematical form to the Ginzburg-Landau effectiveness. So you could make an almost one-to-one translation between what happens in superconductivity and what happens in pion-nuclear physics. So let's look at the terminology of pions. The charged pions were discovered in 47, neutral in 50. They together form a triplet, isospin triplet. Their microscopic theories, quantum chromodynamics, was completed only in 72, 73. But their effective description, like the Gelman-Levy model, was completed in 60. So you see the parallel. The microscopic theory of superconductivity, PCS, happened in 67. The effective theory of superconductivity, the Ginzburg-Landau, was formulated several years earlier. So here is the Gelman-Levy effective theory, and you see that this part looks exactly like the Ginzburg-Landau theory, where instead of one complex autoparameter, we have 4 real autoparameters which transform together in a certain way. So it is Ginzburg-Landau theory when the symmetry is different and are not coupled in any long-range forces. And here is the coupling between nucleons and these 4 particles. And if you look at it, F squared corresponds to sigma squared plus pi squared. But this theory, nucleons are massless, which is completely absurd because the pions which were almost massless and not nucleons, the nucleons are very heavy. But this effectively says the nucleon is almost massless. But that is only illusion, and we will see what really happens. So the sigma squared plus pi squared is invariant under 4-dimensional rotations. And these 4-dimensional rotations can be broken down to isospin rotations and chiral rotations. Now, this symmetry is spontaneously broken if sigma takes a value f pi. This is very similar to what happened in the Ginzburg-Landau theory, where the order parameter Takes seriously, it takes a constant value. Now, the amazing thing is, if you go back and put this, I must really show the equation. Here, if we give a constant value to this, it generates a mass for the nucleon. And the mass for the nucleon is related to the pion nucleon coupling constant. And this is called a Goldberger-Kleeman relation. So, lot of progress about pions without any fundamental theory. Like you see, you can add a symmetry breaking term, and that gives a small mass to the pion. In fact, in the ferromagnet, the Boson bosons are massless, but if you apply an external magnetic field, they behave as if they are massive. If you make the external magnetic field small, then the Goldstone bosons will pick up a small mass. So the explanation now is pions get a mass because of an explicit symmetry breaking. Nucleons get the mass because of spontaneous breaking. Symmetry. Now, axial current is exactly conserved when pion mass is 0, just as the vector current. So this whole asymmetry between axial and vector current is completely removed. Explanation has been given for the lightness of the pion mass, and you see that a lot of things are fallen through. Now you can ask, in the superconductivity, the Goldstone mode disappears completely because the electromagnetism is coupled. They will match in vector field, and the Goldstone boson is gone. Why is it not happening here? That's because in nature, there is no long range analog of electromagnetism that couples to nuclear charge. Whereas in superconductor, there is long range electromagnetism coupling to electric charge. And this also explains why in nuclear physics, the Goldstone boson survives, unlike in superconducting. Now I come to Higgs boson, which is called the God particle. Everybody, when I meet them in a bar, they say, "What is this God particle?" God particle. And I have to tell them, look, in a pub like this, the physicist, he actually wanted to say goddamn particle, but that was considered not a very polite way, so it got sharpened to God particle. And the Higgs boson discovery has been correctly touted as one of the real triumphs. What's the connection between Higgs boson and superconducting? Okay. Now we all know that the Fermi theory of beta decay explained a whole lot of phenomena, but it was not generalizable. And in fact, effective theories are effective only to a certain cutoff. Beyond that, they can behave very badly, and you may have to replace them, modify. Now, the weak interactions were found to have very short range, and this suggested that they too should be described by exchange of massive particles, but now this had to be massive vector bosons, unlike nuclear forces, which were explained by massive scalars, which were the pions. Now, the theory of such massive particles had tremendous theoretical difficulties. I don't want to go through that, And in fact, particle physics and field theory went through some very difficult periods in trying to make sense of the fact that massive vector particles are very, very hard to describe. Now, the final resolution of this was to treat these as analogs of electromagnetic fields of superconducting. So now when we do a superconducting analog of Higgs phenomena, we have to realize in such a way that the Goldstone modes do disappear as in the original superconducting and not survive as they did in the case of ions. So the order parameter was taken to be a complex doublet. There are 4 real fields, and the Higgs potential was taken to be exactly like the Ginzburg-Landau or the Gell-Mann-Levy case. And I am not going to write them down again. The non-abelian gauge invariance renders only the magnitude of the Higgs doublet as physical degree of freedom. The remaining 3 always occur in combinations, just as we saw while explaining Meissner effect in superconductivity with the gauge fields, and these combinations behave in complete parallel between what happens in superconductivity. Somebody should warn me about time. Now, the unexpected bonus of this was that electromagnetism and weak interactions got unified, and in addition to the weak currents, electromagnetic currents, a new type of neutral current. Now, in superconductivity, the amplitude fluctuations, they gives rise to massive excitations. And the analog of that here is you get one massive Higgs boson. And that's the Higgs boson that was experimentally discovered. Fermions get their masses in analogy with the gap in superconductors, and the way nucleons get masses is as in the Gell-Mann-Levy model. First theory proposed along these lines was by Weinberg, Glashow, and Salam, and it was proved to be renormalizable by our Dutch friend Gerard Toft in 1972. And as they say, the rest was history. So here are the pictures. Anglais, the so-called Higgs effect was discovered by many, many people, of whom Francois Anglais was also one. And in the back, you see the same potential that was used in the Ginzburg-Landau theory, Gell-Mann-Levy model. Peter Higgs passed away just a few weeks ago, and he was 95, very unassuming man. And you couldn't tell that he had accomplished so much in his life if you met him in person. The last topic, please. Comes to the third major problem of physics, and that is the problem of particle. Now, Gell-Mann, White, Hans, and Nambu, they all proposed quarks as the constituents of even protons and neutrons and ions, but nobody had seen quarks. Even when you did proton scattering at very high energies, no quarks were seen, and this was seen by some as a major failure of the quark model. Quark model was formulated in 1964, and I wrote a thesis, master's thesis, in this. And there was a viva in which Charge and Yogesh Pati were asked, why are quarks seen? The standard explanation is a very heavy So you're not giving enough energy to these collisions. Then the puzzle was, if they're so heavy, why is the proton so light? So it comes back to the same problem as to why pions, which are seen as bound states of nucleons, were so light. Nobody had an answer to this. And then as you kept jacking up the energy, quarks were not to be seen. So you can't go on increasing the mass of the quark as an explanation. And soon it was discovered that something's amiss. Usually it's only politicians who make a virtue of an embarrassment. But in this instance, even physicists managed to do that. So this embarrassment of not seeing quarks was turned into a principle. With absolute confinement of. So you will say, come on, you're putting me on. Somebody comes and says that you're poor because there's a principle which says you'll always be poor. Okay? So that's not a principle. Anyway, the idea was said that the dynamics of quarks is such that quarks are absolutely confined. What is absolute confinement? If you take a bound state in field theory, you give sufficient energy and you can make it unbound. But protons, ions, no matter how much energy you give, you cannot separate them. This is called an absolute confinement. Sounds like completely crazy. Even science fiction authors don't just not taken such an idea very seriously. So they already said it's unlike strongly bound system, and all the field theory that we knew at the time could only envision bound states. Therefore, no field theory would actually, accommodate a very radical idea called absolute confinement. And it was not at all clear if any quantum field theory can produce such a phenomena as absolute. The breakthrough was that yes, there is a field theory that can produce absolute confinement, and that's a superconducting field theory. Why? Now, imagine the world was filled with superconductors. Now, it's a very, you have to stretch your imagination a lot. And don't ask yourself what happens. In the Ajit movie, it says, sink him in liquid oxygen, and oxygen will not let him die, and the liquid will not let him survive. Okay? So it's this superconductor, but imagination. Now I try to put one magnetic moment. I put only one magnetic moment. Molecular effect wants to get rid of the magnetic field everywhere, but it can't, because if I take a sphere around the magnetic monopole, the flux through that cannot vanish. So the flux of a magnetic monopole cannot vanish everywhere. And you come to the situation like an immovable object meeting an irresistible force, something like that. The resolution is the monopole, the superconducting medium, would be infinitely mass. But now I take a monopole, anti-monopole pair, and the Meissner effect will try to expel the magnetic field everywhere. But flux conservation will says you cannot get rid of it everywhere. So what it does is it allows the flux to be present only in a very thin tube connecting the monopole and monopole. So if you separate the monopole and anti-monopole, energy per unit length increases as the distance And so to completely separate them, you need infinite amount of energy. That's absolute confinement. So there is a field theory which can produce absolute confinement. The question is, does QCD do that? And I'll explain in a moment that this is not a superconductor, but a dual superconductor. Why it's a dual superconductor? Why? Because in a superconductor, it is magnetic fields that are expelled by condensation of electrically charged particles which are the electrons. And this leads to the confinement of magnetic charge. In QCD, we want confinement of color electric charge. So the magnetic electric properties are interchanged, and that is what's called the duality constitution. This means that the condensation condensates to now be of magnetic color, magnetic monopole. Superconductor electron was given by nature, but in QCD there are no color magnetic bonds. So how can this make sense? So I quickly explain. If I take in electrodynamics a dipole, then the electric field is everywhere. Okay. So in the superconductor, if I put a monopole, anti-monopole, then this gets squeezed. This is what we think happens in QCD. But because electric and magnetic charges have to be interchanged, this has to be a dual superconductor. And the way to understand is in QED, the electromagnetic field has no self-interaction. But in QCD, there's a self-interaction, and the idea is that the self-interaction will squeeze them, bring them all here, and you get a thin flux tube. Okay? So that's the explanation, and it'll have uniform energy per unit length, and it leads to a potential which is linearly rising, and that's what one would call absolute confinement. So superconductivity has again come and solved another major problem. Unfortunately, this is too complicated for any analytic work. That is gate theory, which I'm a practitioner for international. This is given a lot of very useful and positive results. And here is the picture from lattice gate theory. Already several years ago, there's a static quark, static anti-quark, and you measure the color fields, and this is what you find. And you come very close to the quark or anti-quark, you will just see a Coulombic peak. Because if you look at the energy density around a Coulomb field, it diverges as you approach the charge. And in fact, there are 8 types of charges in QCD, and the strength of the Coulomb flow is 8 times. So everything fits in. And as you slightly move away from that, the self-interaction between gluonic fields starts producing a decrease. And if you move sufficiently far away from the quark, then you see that flux tube is. So the numerical evidence of flux tubes is very strong. Analytically, we have no proof for that. And in fact, if you analytically prove this, you can get $1 billion because there is the Clay Institute of Quantum Physics, which will give you $1 million. But I think this is just the mathematicians way of frustrating physicists, because no matter what proof you come, they will always say, you treated an unbounded operator very carelessly, and we can't give you the money, we can't give you $1 for this. But don't take the $1 million very seriously. But analytical work has to continue. Finally, I think I just have 2 or 3 more slides. So here this is exactly 20 years ago, I built this Colloquium cluster, and with Pushan Majumdar, who passed away very engaged, we pushed this cluster and got some amazing results for this flux tube, which I'll tell you. What's the result we got? We found that to a high accuracy, the flux tube behaves like a bosonic string. But bosonic strings are meaningful only in 26 dimensions. The QCD is in 3 and 4 dimensions. So is it just a numerological coincidence, or is there something deeper as to why the QCD flux tube is behaving like a bosonic string, even in dimensions which are away from the string theory's 26 dimensions? So this is what I call Kabru's gift. We could push it beyond what other people have done. People like Weiss and Lucier had studied it, and they could only stop somewhere here. But you see, with the help of Kabru, we could push it, and what we found was that the static potential between quarks and antiquarks, very short distances, is given completely by perturbation theory. The moment you go to somewhat larger separations over the Fermi, then that completely breaks down, and the results come closer and closer to the bosonic string theory in 3 dimensions. This was the numerical gift that Kabru gave us. Then with Peter Matlock, who was a postdoc here, and a younger colleague, I developed effective string theory. They said you have effective field theories, you can make effective string theories also, where you don't have to require dimensions to be 26, they are valid in all dimensions, and we could mathematically prove from those effective string theories that the static quark antiquark potential is exactly what you get here. Okay. So this is going beyond absolute confinement. It requires finer understanding of the QCD flux tubes. And this is why I call this story strings to strings. Because the original string theory was born out of S-metric theory of strong interactions. Duality, no one. But that string theory had a lot of problems because it had excitations which were not part of the hadronic spectrum. And that string theory was junk. But they made a virtue of it by saying you're applying the string theory to the wrong problem. That's the theory of everything. Now, I don't know whether you want to believe it or not, but it is still not ruled out. Then comes QCD to replace the string theory. And when we look deep into QCD, formation of flux tubes, and when you study the behavior of flux tubes, they behave like bosonic strings. So, hadronic strings, hadronic strings, the meaning is changed. I think that's talking. Questions? Comments? super
Can
clear?
I ask a stupid question?
I may not be able to hear you, so I'll try to. Over.
Yeah, okay, so basically, I mean, there is in Ginsburg-Landau theory, in Ginsburg-Landau theory, there is this thing where you sort of apply a field and you generate vortices. Okay, and they can also form a lattice, but the point is now that in a superconductor, as long as the thing is a superconductor, the vortices are massive. Okay, but what can happen is that the vortices can proliferate and you can end up in a dual regime where the vortices are superfluid and Cooper pairs are massive. That's a phase transition to an insulator. It's a dual. So the two are dual to each other.
In fact,
So is there a kind of
the
analogy?
QC districts are also like the vortices. And people like Paul Olesen and Nielsen, they had actually shown that field theories can have string-like excitations, and those strings are exactly the Abrikosov vortices of superconductivity. So in that sense also, you see a duality because, we actually need dual superconductivity.
Thank you.
This like Hawks cube behaves like a stream. Is that the open stream or closed stream?
Open or closed strings?
Huh?
Are there open strings or closed strings?
Are there?
Open strings or closed strings?
The QCD strings?
Like Hawks
Yeah, sure. I mean, these are open strings. That start with the part and end in the antic one. But once you set up the effective string theory, you can easily formulate it for closed string forms. Now, whether it can form rings of gluonic fields, now that's an experimental question. Maybe some glue balls can actually be the analog of closed strings.
Further question? Very nice talk. Please talk.
Thank you.
Make a piece.
Thank you for the night.
Reaching the green one.
You can present.
I'm in room 206.
Okay.
So if you tell me a time, then I will get that.
Yeah, so usually I am here by 10:30.
What?
10:30.
Okay, 10:30, 11 will be.
That's fine with you? Okay, thank you.
I have a question like that. If this Hawks cube is a like open string, right? You're saying that. So it's like painting on some deep end or like as you're doing strings, so that's like open string.
Maybe, and I'm sure, I mean, deep rains come because you change the boundary condition.
Yes.
So, no, I don't know.
It's like I'm saying.
Whether they're realizable in
QCD, yes.
QCD.
So that's like,
You can form them mathematically, but
and this bosonic string as usual described and this number products, right? This bosonic string here, you are matching your result in this limit as a bosonic string. So this bosonic string are described as usual this number products, right?
yeah, I mean, we can mathematically do the same
And
everybody does in deep rains. But the question is, are there configurations in QCD to which, they can be applied, and that's not there.
So he's asking, do you apply the Nambu-Goto action or is it a different one he was asking?
No. Number go to action. So there's an effective theory. Okay? So yesterday, for example, this was the standard model action, then various terms were added. In an effective theory, you can add any number of terms as long as they have the correct symmetry. So here also, the class of effective string theories will start with the number go to action, but you can go on adding anything. But you can prove universality that no matter what effective string theory is, You get the first few terms are the same as if it comes from the number coding.
So for effectuation, I also need this while invariance and ectomorphism invariance as in the string cell. So
There are two ways of formulating it. Either you do it in the Nambugoto way, where you only introduce an X field, but not just Nambugoto action. You have to require reparameterization invariant action, and you can write them down. Or as Colloquium did, you can introduce the worldsheet metric and introduce while invariant. So this can also be done for the entire, effective action. Both formulations can be done.
There is one question. Are these QCD strings, when you say that they are like bosonic string, are they relativistic?
Yeah, that way.
But then they should face the same problem of critical dimension. Critical dimension being 26.
No, don't. That's the point.
Why not?
I'll tell you, because this is already known even in string theory. It's called the Colloquium subcritical string theory. It turns out that when you formulate string theory in less than 26 dimensions, there is a conformal anomaly, and when you do the path integral, it is equivalent to introducing an additional field, which is the Liouville field. Now, the Liouville field exactly cancels the conformal anomaly in all dimensions.
Yeah, but now suppose I don't formulate Colloquium. I don't formulate it Colloquium. I do not formulate it like Colloquium. I don't have conformal invariance. I just have a bosonic string, right?
Yeah.
So I have the oscillators.
No, you can have the bosonic string theory and do it in less than 26 dimensions.
I have oscillators only. I have only oscillator spectrum,
Yeah.
alpha mu's, right?
Yeah.
And there are so many of them. Number of space dimensions being D. I start with light from gates where I've done the calculation. And in order to get the covariance, I need to go to critical dimension again.
So it doesn't matter how you do it. For consistency, you will need an additional degree of freedom.
So that is available here. So and then apart from this, there is one more degree of freedom.
And it is such that it exactly cancels the conformal anomaly. So in all dimensions, you get consistent. Price you have to pay is this.
So what is the identification of this extra degree of freedom? What is the identification of the extra degree of freedom?
Is Liouville.
No, in QCD picture, what is the
Same thing happens because so now you write an effective action. Starting is
what I mean is in terms, can it be related to underlying quarks and evolve?
so you start with the Nambugoto effective action. And that theory, even here, will be sick other than 26. Now you add additional terms to the effective action. And you find that when you add a non-polynomial action, adjust the coefficient so that the anomaly, equivalent of the anomaly gets cancelled.
But with extra degree of freedom or no extra degree of
With no extra degree. All
or
X,
just extra terms?
only X. Okay, this is effective theory. And now you see that this non-polynomial action written in terms of X is nothing but the Liouville field where phi is replaced by
Phi is integrated out and you get it.
as the composite operator.
How do you interpret the excitations of your strings in the QCD? How do you interpret the excitations of the strings? I mean, these are,
Yeah, no, there are,
so,
because
so these are gluon degrees of freedom. How do you interpret them?
they're not really blue balls.
They're not blue balls. Okay.
So this is the tricky question. So if you do charmonium, but in charmonium, the quarks are all finite mass.
Correct.
So static limit cannot be taken. But if you make an approximation, then the charmonium excited states would contain these excitations. Of
Oh,
the
okay. So you
string.
start with the CC bar with string, then you get all the excitations of that constant. But it doesn't say anything about blue balls. It doesn't say anything about blue balls. It doesn't say anything about blue balls.
Open strings, somebody asked, closed strings.
Yeah, but
they would
But
do.
that you don't normally see closed strings in.
Because once I have an effective string theory, I can look for both open string solutions and closed string solutions.
Nice.
So the closed string solutions should correspond to blue balls.
But on the lattice, no one has seen these closed string solutions, right? On the lattice, are there any closed string? No, but are they coming from closed string solutions? No, those
Yeah,
string
yeah.
balls are different, right?
Why? They are actually close.
They are close.
They are like packets or something.
I mean, see, the lattice you can study the glue balls.
Yeah.
The question is, can you interpret them as
Huh.
closed strings? of
Exactly,
course?
that's what I'm asking. That is, I don't think it is so straightforward to see that. This is the placket, right? Very nice.
Actually, for this harmonic acceleration studies.
Reminds me of your lectures that you gave us.
Huh?
Reminds me of the lectures that you gave us. in
First
field
course.
theory. First course in field theory. Yeah.
This gets well.
I also given you like.
Yes,
No,
yes,
you're
yes,
not
I
listening either.
know.
You're not listening.
No, amazing. Lot of this stuff. I mean, in fact, yours was the first course which started out with looking at it from the condensed matter perspective. And continued, in fact, even in RG, looking at Wilson's RG was because of you actually that we looked at it. So it was very nice. Nowadays, we teach one course less in field theory. So we never get to this point. It's really sad. We don't teach enough of that. But I guess students will be that.
Otherwise, till age 30, they will be learning courses on get past that.
Three semesters in field theory. So,
Okay, teaching the undergraduate, you have the best of quantum mechanics and quantum mechanics too. You are not got anywhere near where you want to go. That's too 1 year is over.
So, yeah, I can imagine. Yeah.
But it really is quantum mechanics to benefits on of it.
Oh, even relativistic you have not gone to know.
Okay, just disconnect it.
Yeah, you can just disconnect.